Why?
Alright, gravitational force exerts a particular force on every object, and we would call that the force due to gravity. That is also known as something really important called weight.
Wait a minute.
The weight of an object. The weight, by definition, is the force that gravity applies on a particular object. So, you should remember this from physical science, in that weight can change and mass cannot. So, mass can't change because it's the amount of matter something has. Weight can change because it's dependent upon gravity. So when you step on a scale, what you're actually measuring is how much gravity pulls you downward. Okay? And if you were to go up into the mountains, or even better yet, up into outer space, you would notice that your weight is going to be greater, less, or the same?
Less.
Less. Because as you go up in the atmosphere, the acceleration due to gravity, or the gravitational force, is less.
Oh, gotcha.
Okay, so I am just going to quickly put up here, I don't want this to confuse any of you, but this is really the Pt1 equation, just specifically for what?
Wait. Oh, those things, whatever one.
For weight. Okay, it is Pt1, it is Newton's second law. Okay, but it's specifically talking about weight, how you figure that out, and obviously the acceleration would always be the gravitational acceleration, which would be negative 9.81, and your weight should always be a negative force. Now, if they ask you, like, what would be the force that you would need to overcome an object's weight, then it would be like a positive number, if that makes sense. Okay? What?
So the weight scale. Yeah.
Well, the magnitude. The idea of weight is a number is not, right, that doesn't have a direction. When you step on a scale, it doesn't say, yeah, you know, you're 400 pounds downward. Right?
Wow.
So, I know. It doesn't look like that way though. It's all the weight of you guys.
Weight of stress.
Yeah.
Weight of stress.
Okay? Now, weight changes from location to location because gravity can change from location to location. Something that's very important, we've already talked about this, we'll skip that,
Right?
right?
You go in space, there's so much gravity.
Yeah. We're going to skip that. Something that's very, very important, or has a lot to do with weight, is the normal force. And I think we kind of alluded to this earlier, because we've been talking about normal force quite often. Normal force is always going to be the force perpendicular to a surface. So every time you have two objects in contact, the normal force would be the force that the one object would exert perpendicular to whatever surface you're on. So if you were at an angle, like in this case, okay, your normal force would be perpendicular to that surface. That's not perpendicular.
That's not enough.
Anyways, you get that.
Wow, he's bad at drawing.
Laugh at him. Okay, but notice what gravity's vector looks like.
Downward.
It's always straight downward. Okay, so your gravitational force will be straight downward regardless of what your surface is. Okay, so I want to just show you. If you know you're not accelerating vertically, let's just say I got a box on the ground. We know gravity pulls straight down. And if this box is not moving up or down, what must be true about the normal force? Equal. It's got to be equal and opposite. That would be your normal force. Okay? So you could say that Fn equals Fg. Don't write this in. Please don't, because you'll just get confused if you write that in your note card and you don't remember the context for which I was talking about it. Okay? Those will be equal if you're not at an angle and you're not moving vertically. Okay? However, if you are at an angle, you could still find what the normal force is by using this equation. Notice how it's still mg, which is what fg would be, but it's cosine of theta to account for the angle difference. Okay, so what if you weren't at an angle? What would the angle be if you weren't like that?
Angle would be 0. Isn't that what you're asking for?
No, the angle would not be 0.
What's the angle if you're not in an angle?
What's the angle of
90.
90 degree angle? Cosine of 90, so I'm gonna plug it in. What's cosine of 90? It's 1. So do you see how if you're not at a technical angle, you're actually it's 90.
It's 0.
Wait,
It's
0.
It's not one.
What's the angle if you're not in an
0,
angle?
you tingling.
Maybe.
What kind of teacher are you?
I'm still confused here.
How did I mess that up?
Yeah, how did we both get one?
What's the angle if you're not?
Oh, okay. I get what they're saying. Okay, so yes, that would be a 0 degree angle. What's cosine of 0? What is cosine of 0? 0.
Am I right?
Oh, 90. It should be 1, shouldn't it?
Should be 90.
There's 1.
is 1.
Yeah, cosine of 0 is 1.
Yeah.
Okay.
So
That's what I was meaning to say, and I butchered that really bad.
Oh!
Okay? So yes, what they're referring to is that angle, which should be the same as that angle. Okay, and if there is no, if you're not at, if you're not on some incline at an angle, you don't have an angle for your normal force. So therefore it would be 0, and then cosine of 0 is 1, and so therefore Fn would really just equal what? Fg. Well,
So when you're not at an angle, the angle's not 90. So correct? Okay, I was
you tried so hard on that one, Cole. Okay? So, guys, I'm sorry I misspoke, but please pay attention so that you understand what's really happening here. Okay? If you're at an angle, your normal force will be jutted over that same angle just because it's always perpendicular to the surface. If your surface changes, so will your normal force. It will change proportionally. Okay? If you do not have an incline, you have no angle. My bad. Okay? And therefore, I thought for some reason cosine of 90 was 1. So I apologize. Got it?
Everybody makes mistakes. Everybody has those days.
Becomes a little bit more difficult if you have other forces involved, which is what we'll do tomorrow.
How could you?
No.
Yeah. Oh. All right. I'm going to use my super handy dandy demonstration of my stapler. All right. We're going to talk about friction. Consider a stapler. Okay, everyone see? Cool, cool. Stapler is at what? Rest. What can you also say about equilibrium? No acceleration. Net force of? 0. Okay. All right.
Oh, not constant.
So we know from Newton's first law that the net force acting on the stapler is 0. Not accelerating, not moving. Newton's second law tells us that an additional unbalanced force applied to the stapler would cause the stapler to what? Accelerate. Okay.
Oh.
Yes. You can be moving and not accelerating, right?
Alright.
Okay, let's be here. Okay, so would cause the stapler to accelerate and remain in motion unless acted on by another outside force, right? That's what.
Newton's first law.
Yep. Okay. But experience tells us if I apply a small force to the stapler, what happens?
It's gonna accelerate.
Accelerate.
I'm applying a small force.
It
How
won't
small
accelerate.
force? It's not what?
Opposite reaction.
I'm applying a force on this.
What's the point of force on this?
Why is it not accelerating? Oh, who said that? I heard it.
I said like friction.
Friction. I learned it.
We said it like 800 times.
I'm done.
Friction!
Yeah.
Don't let this touch it.
That's crazy. Just
Now, guys, please focus. Okay? So, if I'm applying a force that direction on it, and it's not moving, that must mean there must be some other force that's going in the opposite direction, which is what in this context? Friction. Yes.
What about the force of gravity pushing down?
Yeah, but that's in a completely different plane. So like, we know that the normal force and gravitational force are equal, but if I apply a horizontal force, then there better be some opposing force,
Yeah.
otherwise this thing would move.
So the stapler doesn't exert force, it's
What?
just friction?
The what doesn't?
The stapler doesn't?
I mean, the stapler exerts a force on the ground, but I'm talking about the
I thought it would
stapler.
exert it back, like with the wagon, when the kid was pulling it, the wagon.
Yeah, but those are two completely different objects. I'm talking specifically about the motion of the stapler right now. Okay? I'm not talking about, you're talking about wagon and a kid. Those are two different objects.
Yeah, I was thinking your finger and like you and.
Yes, the stapler is pushing back on my finger. Yes. But because of the fact that I'm resisting that, still my finger's not moving. But I'm not worried about my finger. I'm worried about the stapler here. I'm trying to apply friction to the stapler here. Okay? So if I apply a force, in theory, due to the Newton's laws, it should move that way. Unless there is a net force of 0 horizontally.
Oh.
So if I'm applying a force this way, if there was no other forces, that object would move that way. It would accelerate that way. Which means there must be some force equal and opposite, and we know that that force is the friction force. Okay, let's keep going. If we were to apply a large enough force to get it to move, it eventually what? Stops. And we know that because of what? Friction. Okay? So, the resistive force that keeps the stapler from moving is called static force. Now notice, from moving. It's the force that resists the initiation of sliding. Once we have it moving, it's a different kind of friction that we call kinetic friction. And I want you to know something that's really fascinating. Kinetic friction is always less than static friction. It's true. We're actually going to do a lab tomorrow that will prove it.
Oh, yay, lasts.
Okay? You will actually see that the static friction is greater than the kinetic friction. And it should make common sense. I mean, it's always harder to start an object moving than it is to keep it moving while it's moving.
Plus you can't, Isaac, you can't resist more than not moving,
Okay?
Can't resist more than not moving.
which is what static is.
Correct.
So listen, guys, when you push something, you have to push harder to get it to move, and then as soon as it starts moving, it almost just miraculously appears easier to move, doesn't it? Yeah, it should. And I guess I could, I don't know, figure out something. Push, but I know, Isaac never does anything physical, ever.
Oh!
Except for kick a soccer ball through a
That's
goal.
gross.
Okay? He doesn't care. I don't. Okay, so the point here is, and I know it probably thinks a little counterintuitive, but if you could think back about a time where you pushed an object, typically you should have noticed. I mean, obviously, the bigger the object, you notice it more.
When you push a car.
Yeah, when you try to push a car, it's really hard to get that car going, but as it starts moving, it becomes easier to push. Okay? Yep, that's my card. Alright, so.
You move.
Okay, in free body diagrams, and we're doing free body diagrams with an object that has friction on it, the friction force will always be parallel to the surface of contact. So what that simply means is if this is my surface, horizontal, it will always be parallel to it, and it will always be opposing what? The direction that you are trying to get it to move, or the direction that it is moving. Okay, that should make sense. That's not something that I think would be something that you would not be able to comprehend from just seeing everyday experience, right? Okay, to determine the direction of the static force, we use the principle of equilibrium. What this simply means is remember, static force is before it's moving. So how do you know which way it's opposing if it's not moving? Well, you would use the principle of equilibrium, which simply says if I apply a force in that direction and it doesn't move that direction, you'd have to know equilibriums would be 0 if it's not moving, so therefore you'd have to have a force that would be opposing with an equal magnitude. Okay, so if I were taking a object and I was applying a force that direction, but it wasn't moving that direction, which direction would friction be going?
The opposite way.
The opposite with an equal magnitude.
Or greater.
But still parallel to the surface? All right? Okay. Well, you probably would understand this as soon as I state it, but friction kind of depends upon the material, doesn't it? Some materials exert more friction than others. Due to, yep, you will want to put these two equations on your note card. And that says Fs max, which just means the static friction is max. Because really what you're doing when you're doing static friction is there's a point where you can exert enough force to overcome static friction. That would be your Fs max. Fs. S for static. That's just the Greek symbol like mu or something that they use.
Don't you remember that math?
Yeah.
Do we remember that?
Greek symbol mu, and then it's the symbol we use for the coefficient of.
Isn't that a Greek picture of U?
Yeah. What did you say, Avery?
Teardrop U.
Yep.
What people call it.
And so you can probably understand that there's a relationship between friction and the normal force only because there's a relationship between the normal force and gravity. Because you would experience the harder the objects are pressed against each other, the more friction you have. Try like just putting your hands together and going and just, moving your hands quickly. You got friction. Push your hands harder together and do it.
Fight the friction.
Oh, it's harder.
And what do you notice?
It starts to burn
Yeah, because there's more friction.
and smell like a burnt hot dog.
Wait.
What
did you say?
Okay? So the point is, guys, things that are more massive are going to have more friction on it.
On my word.
Because gravitational force is going to be pulling down, and there's going to be more, more weight. It's going to cause the object to have more friction. Or it's going to really compress the space between the objects more. So there's more surface area in contact. Okay, so what these are used for is to figure out, these coefficients of friction are going to be really dealing with your surface. So I want you to, I think in your book there should be a table that has the coefficients for each object. What page is that?
Might not be a full complete page, but it's also.
We only have
We have some in our notes, so that's right.
Do I? Oh, those are, okay, that's, never mind, the ones in your notes are I probably just took them right out of the book. Okay, so you can kind of see steel on steel, aluminum on steel, rubber on dry concrete. Now obviously this isn't an exhaustive list, but you should have enough of these to be able to answer any problems dealing with this. Okay?
No, that's not on this one.
What is dry snow?
Yes. Snow versus dry.
Yes.
What's the difference
It's like
between the
dry
UK
ice
and the FK?
UK is the coefficient. It's really the material itself.
United Kingdom.
There's kinetic and static.
So-
There's one for you.
Yeah, but.
What the U symbol is referring to is how your surface plays an impact on your friction. And that's what the equations are showing you here. So let's assume we're doing this problem here. Okay, we got a 24 kilogram crate initially at rest on a horizontal floor requiring 75 newtons of horizontal force to set it in motion. You notice how it said 75 newtons of horizontal force to set it in motion. Okay? So that would be your Fs max, because it was the amount of force that you needed to overcome that friction.
And then your weight is 24 kilograms. Wait, cramps.
Okay?
Cramps.
And we know, yeah?
It says Fx comma max.
Yeah, fine.
Whoa.
So it's like,
This is typo.
it's still the same thing.
Yeah.
So then Fn is 24.
Okay, so we got an equation for the static coefficient. It's that max over Fn. Okay? It wants us to find the coefficient of static friction. It gave us Fs max, but it didn't give us directly Fn.
couldn't you find
What's that stand for?
What's that for?
Net force?
Force.
The N here?
Yeah.
Normal force.
Isn't the Fn just the amount of stuff that you're putting on the
Yep. Yep. So what you would do to find Fn, first of all, Fn is going to be mg cosine of theta. Well, we're talking about a horizontal floor, so what would be the angle, guys?
0.
0. So cosine of 0 is 1. We can eliminate that. Doesn't this just look like what the force of gravity would be?
Yeah.
Okay. Right. So gravity's pulling down. The normal force would be an equal and opposite force. So if we find the gravitational force, what do we find? The normal force. Okay? So the gravitational force then would be your mass, which is
24 kilograms.
24 kilograms,
Oh yeah.
and your gravity would be negative 9.81. For the second time, I'm just going to give it to you. It would be negative 235.44, but the normal force would be the opposite of that, so it would be a positive 235.44, correct?
Yeah.
Everyone following?
No.
We write
I thought we were finding Fn.
What was that?
I thought that equation did equal Fn.
Sure. Then you could say that that would just be not negative.
Why'd you switch to this equation?
Which equation?
The one on the one.
Well, because I need to find Fn.
Well, where'd you get that equation from?
This one? This is the normal force equation. Fn equals
Do we write this
mg
down?
cosine of theta.
Write that down.
Oh, I don't have that right.
It just came up today.
Oh, was that first one on note card?
Every equation that you see should go on your note card immediately. Okay? This really should be a. I'm just trying to show you the relationship between Fg and Fn. Okay, that's what I'm trying to do here. Okay, we know the Fs max is 75 newtons, and we know the normal force in this context is 235.44. We can figure out what the coefficient of static friction is, and it's 0.32. Now I'm guessing if you looked on your in your sheet, you can figure out what it is that we're on.
Ice on ice. Right now, that's my overview.
It doesn't have anything, does it?
Wood on wood is 0.4.
Those are all static.
I would say it's probably close to. Yeah, it doesn't tell us. It's a crate, so I would guess it's probably pretty close to wood on wood, but it doesn't appear to give us enough information for us to tell us what this is.
That has no like label to it.
Nope, because Newton and Newton would cancel.
So it's just a
ratio. So what these coefficients of friction are ratios to figure out how much is this going to move. Yes.
What's the cosine of theta? What was that?
Cosine of theta in this case is cosine of 0. Because
So why isn't it a negative 9.8?
well, it is if we were solving for gravity. This would be Fg. This would be
I get what it's 0. I was just asking because I was seeing it as a negative, and that's how we got
Well,
it.
Fg would be negative, and it's going to be opposite Fg. So
It's on.
Be positive. So that equation, this G,
Around me, I'm
when
standing
you
there.
see
Hey, boo.
instead of seeing A, G, like accelerated through gravity, you just see G. That's just the negative.
Yes, you do.
No,
No, it
it's
doesn't.
just the positive.
No, I'm saying, will it see me if I go like this?
Maybe not. Keep going. You're good. You made it.
The acceleration through gravity, that would be negative.
That would be negative.
Yep.
Have you listened to the new tunes yet, Kramer?
You what?
The new tunes?
What new
What are you doing?
Oh, I have not.
Ugh.
Oh, yeah.